Um, Towards the end of our last session on kinematics, I got you introduced to some basics of relative motion, right? I said, if there is a particle A that has a velocity VA, and a particle B that has a velocity VB, this system could be reduced to a system in which, let's say, A or B could be used as an observer, right? That means if I choose to have A as an observer, A on itself will not report any velocity. So if A is an observer, it's as if A is pinned, A is brought to rest equivalently. The system could be reduced to a system in which, as if, say, if A is an observer, if A is looked upon as an observer, that means A is pinned, then the velocity of B as observed by A, is said to be relative velocity of B with respect to A, That means in a frame of reference attached to A, the velocity of B reported will not be VB. It would have to get modified. It would have to get modified to the extent of minus VA. To VB, you would have had to add minus VA. So if this is VA, VA would be like this. Right? So minus VA would be a vector like this. This would be a vector minus VA. Right? The resultant of these two vectors, VB and minus VA, they need not be perpendicular. This vector, which is velocity of B with respect to A, or relative velocity of B as seen by A, is what A would perceive on B. Right? So, velocity of B with respect to A, that means relative velocity of B where A is an observer. Relative velocity of B where A is an observer is going to be velocity of B minus velocity of A, where A is an observer, and A would not report on B a velocity VB, but the velocity of B would get modified to the extent of minus VA. So then, the absolute velocity of B, this is the absolute velocity of B, this is the relative velocity of B, yes or no? This is relative velocity of B this says, in a loosely speaking sense, absolute velocity of B is going to be given by relative velocity of B. That means velocity of B with respect to A, this is relative velocity of B, plus the velocity of A, which is the observer. Yes or no? The absolute velocity of B is going to be given by relative velocity of B with respect to A plus the velocity of the observer. This observer reports on B this velocity. So if you add these two velocity, you get the absolute velocity of B. This is what you get. To relative velocity, if you add the velocity of the observer, you get the absolute velocity of the particle. Yes or no? Right? Now, say we're going to deal with what's referred to as riverboat problems. Now, some terminology associated with riverboat problems. When they say velocity of boat in still water, what it really means is velocity of the boat as observed by the water. Every time they say velocity of boat in still water, they actually mean velocity of boat as seen by water, right? That means this must be about relative velocity of boat with respect to water. This must be relative velocity of boat with respect to the water or river, right? So velocity of boat in still water, the terminology really means relative velocity of boat with respect to water. Relative velocity of boat with respect to water. This is what it means, right? Say, this is a river flowing. We will assume for simplistic considerations the river to be flowing parallel to the shore. All right? And velocity of boat in still water is relative velocity of boat with respect to water, right? Also, when someone says a boat is being steered in a certain direction, a boat is being steered in a certain direction, that direction actually measures the direction of the relative velocity of the boat. If someone says a boat is being steered in a certain direction, that means the steering of the boat is tilted to an extent that it would want to flow in that direction. Not that it actually flows in that direction. It would want to float in that direction. Then that direction will always give you the direction of the relative velocity, not the direction of the absolute velocity. That means velocity with respect to the river or the water, right? Now, say these are the two shores, and say separation between the two shores is d units. And a boat starts from this point P. And one attempts to steer the boat, let's say, at an angle theta in this direction. One attempts to steer the boat at an angle theta in this direction. Then this direction will measure the relative direction of the relative velocity of the boat. This direction will measure the direction of the relative velocity of the boat with respect to the river. Say, let me call VBR is velocity of boat with respect to the river. Velocity of boat with respect to the river. And say this is the direction. Right? This is the direction of the relative velocity. And say this is the direction of the velocity of the river. So river is the observer, and what does the observer observe on the boat? It observes this velocity. So this is the relative velocity of the boat, observed by whom? By the river. So if I add this velocity to this velocity, what would I get? I would get the absolute velocity of the boat. That means velocity of the boat as seen by a person on the shore. This is what it means. The velocity of the boat as seen by a stationary observer on the shore. This is what it would mean, right? So, if I add the relative velocity of the boat to the velocity of the river, I get the velocity of the boat in the shore frame of reference. This is the velocity of the boat as seen by the shore observer, as seen by a stationary shore observer, right? So, eventually, this is the velocity of the boat with respect to the river. This is the velocity of the river. And the resultant of these two will give me what? Velocity of the boat. The resultant of these two will give me the velocity of the boat. That's the whole idea. That's the whole idea. Right? So, for a person sitting on the shore, even though the boat is being attempted to be steered at an angle theta like this, it would look like going along this line with respect to a person on the shore. A fixed observer on the shore would find the boat to be actually headed in this direction. To be headed in this direction. This is what it would appear. Right? Now, this is the basic idea. This is really the basic idea. The idea is very simple, right? The vertical component of VB causes displacement perpendicular to the shore. The horizontal component of VB causes the displacement of the boat parallel to the shore as observed by a shore observer. As observed by a shore observer. Yes or no? Right? Now, now, say, this is a shore (5 kilometers in width). Okay. And the river flows, say, at an angle of obviously horizontally with a velocity of 4 kilometers per hour. Let's say that's the velocity of the river. Parallel to the shore, 4 kilometers per hour, right? And it is being attempted to steer the boat. The boat has a velocity in still water equal to, say, 5 kilometers per hour. Is the velocity of the boat in still water. That means what must this measure? Relative velocity of the boat with respect to the river. Not the absolute velocity, but the relative velocity of the boat with respect to the river. So, velocity of boat with respect to the river has a magnitude equal to 5 kilometers per hour. Right? And it is being attempted to steer the boat. It is being attempted to steer the boat at an angle theta with respect to the perpendicular between the two shores. Right? Okay. Now, the resultant of the relative velocity of the boat and the velocity of the observer will give me what? Velocity of the boat in the shore frame of reference. Right? Resultant of these two will give me the velocity of the boat in the shore frame of reference. Right? Now, in order to find the resultant of these two, we could resolve these vectors perpendicular to the shore and horizontal to the shore. So, the relative velocity in this direction is going to be VBR cos theta, and the relative velocity of the boat in this direction is going to be VBR sin theta. Yes or no? Right? Now suppose this was the x direction and this was the y direction. If I add all these vectors, VBR cos theta, VBR sin theta and VR, what would I get? I get the absolute velocity of the boat in the shore frame of the reference. So in the shore frame of reference, shore observer, the velocity of the boat that means now the resultant of these vectors VBR and VR, velocity of the boat along the x direction Vx, x component of the true velocity of the boat, x component of the true velocity of the boat would be 4 minus VBR sin theta, 4 minus VBR sin theta. Yeah, please come on. 4 minus VBR sin theta, where VBR is given to be 5, say. Right? Yes or no? The y component of the true velocity of the boat would be the resultant of all these vectors in this direction, which is going to be VBR cos theta, which is going to be VBR cos theta. VBR is 5, so this is 5 cos theta. Yes or no? Right? Now, putting these facts in perspective, can I wipe this off? Effectively, from the ground frame of reference or the shore frame of reference, the boat starts at this point. Let me call it the origin. Let me refer to this as the x direction. Let me refer to this as the y direction. The boat has a vertical velocity as seen in the shore frame of reference. As seen in the shore frame of reference, has a vertical velocity 5 cos theta. What does this velocity do? It causes a drift in the y direction, right? And has a horizontal velocity which is 4 minus 5 sin theta. What does this velocity do? It causes a displacement of the boat in the x direction, right? Now, realize that the displacement of the boat in the x direction in t seconds. In t seconds, the displacement of the boat in the x direction is going to be given by what? Is going to be given by Vx into t. Is the displacement of the boat in the x direction in t seconds, which is 4 minus 5 sin theta into t. What's the displacement of the boat in the y direction in t seconds? 5 cos theta into t. Right? Under the influence of Vx and Vy, the boat moves. This is the net velocity of the boat, which is the resultant of Vx and Vy. This would be the net velocity of the boat, which would be root Vx squared plus Vy squared, right? Right? T seconds later, the boat arrives at a point, say M, that has coordinates x comma y. X comma y means by this time the boat would have undergone an x displacement x units given by that, and displacement in the y direction at the behest of the vertical component of the velocity Vy. This is y, right? This x is caused by Vx, this y is caused by Vy, where Vx and Vy are horizontal and vertical components of Vb. Vb would be root Vx squared plus Vy squared. Now, eventually, when the boat reaches a certain point on the opposite shore, let's say N. When the boat the opposite shore N, a point on the opposite shore, what happens to the y displacement in the y direction? It will be d units, isn't it? On reaching this d, I wrote as what, some 5 kilometers, right? So on reaching N, what does y become? 5, right? Isn't it? Displacement in the y direction will become 5, right? So time taken to reach N, time taken to reach N. In order to reach N, what has caused the particle to reach N? 5 cos theta, acting for how long? T seconds, right? So 5 kilometers to be covered by Vy. 5 kilometers to be covered by Vy. How long will it take? 5 divided by Vy? 5 divided by Vy, right? So time taken is going to be 5 divided by Vy, which is 1 by cos theta. Yes or no? Now, when would this time be the least? If you want the particle to reach a certain point on the opposite shore in the least possible time, and you are allowed to vary theta, then this theta, cos theta, should be 1 for Tn to be the least. Cos theta should be 1 for Tn to be the least, right? That means theta must be 0 degrees. That means he must attempt to steer perpendicular to the shore. He would attempt to steer in this direction. In this direction, theta is 0 degrees is this direction. So if he attempts to steer in this direction, he will reach a certain point on the opposite shore in the least possible time. In the least possible time. Clear? Now, suppose this is where the boat starts, under the influence of a Vx, which is this, and Vy, which is this. And you want N to be a point here. Let's say you want the particle, the boat, to reach this point N prime. Now, in order that it can reach N prime, realize that its drift in the horizontal direction must be 0. X must be 0. Yes or no? Right? To reach N prime, X must be 0. Right? In order to reach N prime, X must be 0. Right? So if X is 0, that means 4 minus 5 sine theta must be 0. Or that means he must attempt to steer the boat at an angle theta with respect to the vertical, such that sine theta is 4 by 5. Right? So if it tries to drive the boat at an angle theta with respect to this vertical direction such that sine theta is 4 by 5, then the velocity of the river in this direction and the horizontal velocity of the relative velocity in this direction will cancel off. Therefore, there would be no drift in the x direction. Vx will become 0. If Vx is 0, the particle will still move just vertically. It will not get drifted parallel to the river, right? Huh? I'll explain. Look. This is the relative velocity of the boat, which is 5 kilometers per hour like this. This is the velocity of the river, which is 4 kilometers per hour like this. And he is attempting to steer at an angle theta. This is not the absolute velocity, this is the relative velocity. If to this velocity I add this velocity, I get the absolute velocity, right? So now, the resultant of these two vectors is a vector 5 cos theta like this, and is a vector 4 minus 5 sin theta, right? Clear? This causes vertical drift, this causes horizontal drift. This is the velocity in the x direction, it will cause drift in the x direction. So if this velocity becomes 0, there would be no drift in the x direction. It will only drift vertically. That means when 4 is 5 sin theta, that means if sin theta is 4 by 5, it will not drift horizontally, it will reach a point on the opposite shore, right? Let me change this situation a little bit. So far so good, right? So, for least drift in the x direction, sin theta is 4 by 5, drift in the x direction will become 0, right? Let me change the numbers a little bit here, okay? So the least drift in the x direction would occur if he attempts to steer at an angle sin theta equal to 4 by 5. May not always be the same set of dynamics. See how things change if I slightly alter these numbers, okay? Say again, this time the river moves, let's say, to the right with a velocity of 5 kilometers per hour, okay? And you attempt to steer the boat at an angle theta such that, so VBR is 4 kilometers per hour. VBR is 4 kilometers per hour. So this is what you try to do here. And again, resultant of these two, relative velocity of boat and velocity of river, will give me the velocity of the boat in the shore frame of reference, okay? So, its vertical component 4 cos theta, horizontal component, resultant of these two will give me the horizontal component of the true velocity of the boat, which means 5 minus 4 sin theta. And say D is the width of the river. Now, he starts from this point, say P. Question is, and these are now the true velocities in the x and the y direction. So they would measure the true displacements with respect to this fixed point along the x and the y directions. Yes or no? Now, if he has to reach, let's say, a point Q on the opposite shore like this. In order to reach Q, the displacement in the x direction must be 0. And first of all, how long does it take to reach a point on the opposite shore? So time taken to reach a point on the opposite shore, any point. To reach a point on the opposite shore, what's the vertical displacement? D. To reach any point on the opposite shore, the displacement vertically must be D. And what causes D? Vy causes D. Vy causes D, right? So time taken to reach a point on the opposite shore is going to be D divided by Vy. Right? Now, in this time, you want the particle to have 0 drift in the x direction. To have a 0 drift in the x direction. That means in order that it reaches Q, x is 0 on reaching Q. But to have 0 drift in the x direction, velocity in the x direction must be 0. Right? But this time, can Vx be 0? That's the question. That means Vx is 0 will give me sin theta equal to 5 by 4. Boom, boom, boom. Is it possible? That means what? If this is not possible, he cannot reach this point on the opposite shore no matter what theta. Because irrespective of theta, sin theta cannot exceed 1, right? See, I just changed the numbers. 4, 5 became 5, 4. That's all, right? But this time, no matter what angle he tries, it'll all be in vain. He will never be able to reach the point on the opposite shore. Yes, yes. So if the velocity of river is more than the velocity of the boat with respect to the river, if the velocity of river is more than the velocity of boat with respect to the river, he will never be able to reach a point on the opposite shore, irrespective of the angle theta that he tries. Right? He will always get drifted horizontally. Clear? Yes or no? Now, so this is not possible, but nevertheless, he will still reach some point on the opposite shore, right? Say, he reaches a point Q prime on the opposite shore. And to reach Q prime on the opposite shore, this must be the time taken. This must be the time taken to reach a point on the opposite shore. Vertical displacement is D at the rate of Vy meters per second. So time taken to reach Q prime would be D divided by Vy. Yes or no? Right? D divided by Vy. Now, in this time, let's say the displacement horizontally is x. This displacement, the horizontal drift is x. And what causes x? X is caused by Vx. Acting for how long? Acting for these many seconds. X is caused by x drift in the x direction. X is caused by Vx acting for these many seconds, because this is the time to reach Q prime. Yes or no? Yes, right? So the x of Q prime, that is going to be Vx, which is 5 minus 4 sine theta, acting for how long? D by 4 cos theta seconds. Yes or no? Yes, sir. Yes, sir. Now, so far so good, right? So far so good. No confusion. Now, if I change theta, then x will change. Horizontal drift will change, right? You know, this fellow, this boatman is a smuggler. he has a treasure here. But unfortunately, he tried hard. He couldn't reach this point directly. Couldn't reach this point directly. In this situation, couldn't reach this point. The earlier smuggler did. Right? This one couldn't. So now he's in a rush to reach this point. If he's in a rush to reach this point, this x must be minimized. He must then have a choice of theta such that this x becomes the least it could be. Yes or no? In order that he can quickly grab the treasure here and escape to glory. Right? So which means now he needs to decide the value of theta such that x is the least it could be. He doesn't know trigonometry, otherwise why would he be a smuggler? Right? So he comes to you, IIT JEE aspirants. He says, okay, tell me the value of theta so that this x is least. I will give you 0.00005 into 10 to power minus 5% of the treasure that is there, which also is huge. Percentage ठीक आता है. Okay. नहीं, loss of indices वगैरह सीख लिया था. Trigo नहीं. By the time it came to Trigo, he became a smuggler. Mega city का. All right. So he needs to work out a value of theta such that this x is the least it could be. Clear? So we can help the smuggler out and report to the police. So for x equal to x least, we want to select theta. That means now what is our x? X is 5 sec theta minus 4 tan theta into d divided by 4. This has to be the least. Now for this to be the least, 5 sec theta minus 4 tan theta has to be the least, right? This has to be the least. Let me call it k. Let me call it k and find the least value of k. Let me call this k and find the least value of k for different thetas, right? A certain theta will give me the minimum value of k. Yes or no? 5 minus 4 sin theta is k cos theta on multiplying by cos theta throughout. 5 minus 4 sin theta is k cos theta. Or 5 equal to k cos theta plus 4 sin theta. Yes or no? Hey, recall trigonometry. A cos theta plus b sin theta is always less than or equal to root a square plus b squared. Yes or no? A sin theta plus b cos theta, this will always be less than or equal to root k squared plus 16. A squared plus b squared, yes or no? Right? Such must be theta, such must be k. So far so good? Yes or no? Which means k squared plus 16 must be greater than or equal to 25. k is a positive number. K squared therefore must be greater than or equal to 9, or k must be greater than or equal to 3. K is a positive number, right? Which means what is k minimum? K minimum must be 3. Yes or no? Yes. Right? So we've been able to find the minimum value of 5 sec theta minus 4 tan theta. That turns out to be k equal to 3. Right? K turns out to be 3. Now, a cos theta, it's the drift in the x direction, isn't it? It's positive only, isn't it? So, our x was like a 5 sec theta minus 4 tan theta into d by 4. That was our x. X would be least when this is 3. Yes or no? This was k. This turns out to be 3. X would be x least when 5 sec theta minus 4 tan theta is k minimum, which is 3. Yes or no? Or I end up getting 5 sec theta. Let me obtain theta for which this becomes 3. Let me obtain the value of theta for which this becomes 3. 5 sec theta whole squared is 3 plus 4 tan theta whole squared. Or 25 sec squared theta, which is like 1 plus tan squared theta, equals 9 plus 24 tan theta plus 16 tan squared theta. Yes or no? Or 9 tan squared theta minus 24 tan theta plus 16 is 0. Or we have like, this is a perfect square, as you can see, 3 tan theta minus 4 whole squared is 0. Yes or no? This is 3 tan theta minus 4 whole squared, right? So this gives me tan theta equal to 4 by 3. Such must be theta. Tan theta equal to 4 by 3. Such must be theta. Yeah, same tone, same person. We'll handle that later. So if he attempts to drift at an angle theta such that tan theta is 4 by 3, then he would reach a point on the opposite shore, very close to the opposite point, very close to the opposite point. Clear? Drift in the x direction would be the least for such a value of theta. Clear? Now, this was the riverboat issue. Now, a little bit again, you know, the same idea. A little bit now on the umbrella rain problems, you know, very similar stuff. So, see, if there is a man moving along the road with the velocity of Vm, right? And rain falls with a velocity Vr. This is the true velocity of the rain. This is the velocity of the man, right? But the velocity of man, if the man was stationary, this is the velocity that he would observe of the rain. But the man is moving. So the man observes a velocity of the rain as seen by the man is going to be velocity of rain minus velocity of man. This is what the man would perceive on rain, right? That means to the velocity of rain, if you add negative of the velocity of man, to add negative of the velocity of the man, this is the velocity of rain. To it, you add minus Vm. If Vm is like this, minus Vm would be like this. This would be minus Vm. And then the resultant of these two vectors would give me velocity of rain with respect to the man. Resultant of these two using triangle law vectors is going to be this. This is velocity of rain with respect to the man. Velocity of rain with respect to the man is like this. The resultant of these two vectors. Yes or no? Right? That means now the manner in which he must hold the umbrella is so as to counter what he is perceiving. He has to hold the umbrella like this along this line so that he gets protection from the rain. Right? In order to get protection from the rain, he must hold the umbrella like this so that he gets velocity of rain with respect to the man. That is how he must. Now, of course, while protecting himself from the rain, if he starts to do this calculation first, then he's gone, right? Now, let me illustrate a few problems to you. You know, there is a sheet titled Sheet 1, Kinematics Sheet 1. Look at problem 7. Look at problem 7. To a man walking at the rate of 2 kilometers per hour, there is a man walking at the rate of 2 kilometers per hour. This is kinematics sheet 1. Velocity of man is 2 kilometers per hour, let's say, to the right. Rain appears to fall vertically. That means the relative velocity of rain is vertical. Appears means what appears to the man. What appears to the man is relative velocity of rain with respect to the man, right? So, velocity of rain with respect to the man is like this. Velocity of rain with respect to the man is like this. This is the direction of the velocity of rain with respect to the man. That means, look, if velocity of rain with respect to the man is added to the velocity of the man, this is the relative velocity of rain, this is the velocity of the observer, the man is the observer. What would you get? You get the true velocity of the rain? Yes or no? Isn't it? So, this is the relative velocity of rain, this is the velocity of the observer. If I add these two, what would I get? True velocity of rain, right? That means the true velocity of rain from triangle law vectors would be this. This would be the true velocity of rain. Yes or no? Clear? Now, even if the velocity of man changes, the true velocity of rain will remain like this only, right? Now, the next part is he doubles his speed. He doubles his speed. on doubling the speed, that means when this becomes 4 kilometers per hour, velocity of rain will not change. But velocity of rain with respect to the man will change. If the velocity of the observer changes, the relative velocity of rain will change. Yes or no? So this time, he's doubling his own velocity. His velocity is becoming 4 kilometers per hour. Velocity of rain will not change, but relative velocity of rain with respect to the man will change. And it's given that when he doubles his speed to 4 kilometers per hour, rain appears to meet him at an angle 45 degrees, right? Which means what I do is, this is velocity of rain with respect to the man. See, it's about time you learned how to be effective in drawing your velocity diagrams. Okay, this is 2 kilometers per hour. I add another 2 units length to this vector. Say, this was velocity of man. This length was 2 kilometers per hour. I add another 2 kilometers speed. Marker. This AB. The vector AB represented 2 kilometers per hour, the original velocity of man. And say CB represented 4 kilometers per hour. I have added another 2 kilometers of vectors. Right? CB represented as final velocity vector. Yes or no? See AB, which was his original velocity vector, 2 kilometers per hour. CB, which was his final velocity, which is 4 kilometers per hour. Yes or no? I hope you understand what I have done. Right? So now, the new velocity of the man is CB. Velocity of rain is this. Yes or no? Yes. Would you then not realize that the new velocity of rain with respect to the man is going to be like this? This is the new velocity of rain with respect to the man, because this velocity plus this velocity, this is velocity or new velocity of rain with respect to the man. This is the velocity of the man, new velocity of the man, 4 kilometers per hour. The resultant of these two must give me velocity of rain. Yes or no? So this would give me the new velocity of rain with respect to the man. New velocity of rain with respect to the man. And that's known to be at an angle of 45 degrees with the vertical. That means rain appears to fall now at an angle of 45 degrees with the vertical. I hope all of you understand this. This is the new velocity of man. Rain now seems to be falling like this at an angle 45 degrees with the vertical. So new velocity of rain with respect to the man plus velocity of man will still give me the old velocity of rain. Yes or no? Yes. Now, I need to calculate VR. The physics is done. Ordinary mathematics is left here to be taken care of. This length is 2 units. So now, this length will also be 2 units. Why? 45 degrees, 90 degrees. So if this is 2 units, this must also be 2 units. This is 2 units. And therefore, this VR must be 2 root 2 units. Yes or no? Yes, so the velocity of the rain is 2 root 2 kilometers per hour. And if this is 2, this is 2. Can you tell me what must this angle be? 45 degrees. This angle must be 45 degrees. So the true velocity of the rain is 2 root 2 kilometers per hour, making an angle 45 degrees with the vertical. Making an angle 45 degrees with the vertical. Yes or no? Yes, sir. Make sure you understand this right now. You know, these velocity diagrams, effectively drawing these velocity diagrams is important to know. Okay, let me illustrate another problem so that you know, very similar problem, but Sorry? Where? Okay, you take this 45 degrees, so this will also turn out to be 45 degrees. Okay, then of course there would be ambiguity, then they would say, in this case it didn't matter. Right? That's why I'll give you another problem in which, you know, your ambiguity will get clarified. Then they would have to say if it's with respect to horizontal or vertical. Since it was 45 degrees, there was no issues. Let me look at problem 16, which is a very similar problem, just different numbers. I want you to get used to the velocity diagram in these umbrella rain problems, right? Number 16. When a car is moving at 45 kilometers per hour on a level road, this is 45 kilometers per hour. This length is 45 units. I mean, the length of a vector is proportional to its magnitude, isn't it? This is how we represent vectors, right? It doesn't mean that this length is 45. It means this length is proportional to 45 kilometers per hour. The raindrops appear to hit the windshield at an angle 45 degrees with the vertical. See, Shramana, this time it's given with the vertical, so there is no ambiguity. So if the car moves like this, raindrops, seem to hit the windshield. That means this must be the direction of the relative velocity. This must be the direction of the relative velocity, and that's known to be 45 degrees with the vertical. 45 degrees with the vertical. This is the relative velocity of rain with respect to the car. Raindrops seem to be hitting at an angle 45 degrees with the vertical. Seem to be means it must be relative velocity of rain with respect to the car. This is the velocity of the car, 45 kilometers per hour. Right? Now, he increases his speed when the speed of the car is increased to 60 kilometers per hour. This angle becomes 60 degrees. Okay, first of all, this is the velocity of rain with respect to the car. This is the velocity of the car. If I add the relative velocity of rain to the velocity of the observer, what would I get? The true velocity of rain, right? So for sure, from triangle law, this must be the velocity of rain. This must be the velocity of rain. Velocity of rain with respect to the car plus velocity of car, which is 45 like this. The resultant of these two vectors must be this vector, must be the true velocity of rain. Right? Now, the speed is increased to 60 kilometers per hour. That means to this vector, I'll add another 15 units. Let me add it in this direction. Velocity of rain will remain the same. Velocity of car will become now 60. Add another 15 units to this vector. That means now this becomes the new velocity of the car. This becomes the new velocity of the car, 60 kilometers per hour, with 15 appended to 45. Yes or no? Right? The relative velocity of rain now This is the new relative velocity of rain with respect to the car. And this angle, instead of 45 degrees, will become 60 degrees. That means this is 15 degrees. Yes or no? Yes. The new angle becomes 60 degrees. Yes or no? Right? Now, I want to be able to find the velocity of rain. Given this data, I want to be able to find the velocity of rain. Again, this is the old relative velocity of rain with respect to the car, plus velocity of car will be velocity of rain. This is the new velocity of the car, 60 kilometers per hour. This is the new relative velocity of rain. So to relative velocity of rain, if I add velocity of car, I get the velocity of rain, which is the same, which is not going to change, right? Now I want to be able to calculate VR. I want to be able to calculate VR. So it's now about very ordinary trigonometry, very ordinary algebra now. Say this length is A units. This length is A units. Then this length must also be A units? Yes or no? Say this length is B units. Then, very clearly, A plus B is 45. Right? And 15 plus A divided by A would be tan 60 degrees. 15 plus A divided by A is tan 60 degrees, which is A root 3. Yes or no?
Yes, sir.
So you can obtain A from these considerations. Plug in the value of A and you can obtain B from these considerations. Yes or no?
Yes.
Right? One could solve for A and B readily from these considerations. Now once you know A and B, then the problem is done, because if you know A and B, VR would be root A squared plus B squared. Do you see that? VR would be root A squared plus B squared. Right? And VR would make an angle theta with the vertical, such that tan theta is going to be B by A. Yes or no? You comprehend this velocity diagram properly? It's just like using triangle law of vectors properly, but drawing your velocity diagrams aesthetically. That's all. Clear?
Very similar to height and distance problems.
Yes. Yes. Clear? Now, see another situation related to relative velocities. Say there is a particle A and its position vector is r1. There is a particle A at time t equal to 0, its position vector is r1. Right? And it has a velocity v1 like this. There is a particle B which at time t equal to 0 has position vector r2. R1 and R2 are known. And let's say velocity of B is V2 like this. I want to know if the two particles will collide or not. Assuming they move with constant velocities, I want to know if particles A and B ever collide, right? So I want to figure out whether A and B ever collide. This is what I am seeking to find, whether the two particles A and B would ever collide. Now, let me reduce this to an equivalent relative velocity problem. Let me reduce this to an equivalent relative velocity problem, right? Where, say, I make A the observer. I make A the observer. So, if I make A the observer, then the velocity of B would be VB minus VA. Yes or no? That would be the revised velocity of B. VB minus VA. So, if A is chosen as an observer, this is an equivalent situation. Equivalent situation. A is an observer. Then the velocity of B will no longer be V2, it's going to be V2 minus V1. See, V1 was like this, so minus V1 would be like this. Yes or no? See, this was V1. This was V1. So minus V1 would be this vector? Yes or no? So V2 plus minus V1 would be the velocity of B with respect to A. Yes or no? Right? So velocity of B as seen by A is velocity of B minus velocity of A. Yes or no? So A, if you imagine it to be fixed, the velocity of B then would be modified to the tune of minus V1. V2 minus V1 would be the revised velocity of B. Right? Now, no. So imagine that A is at rest. Imagine that A is at rest. Then B has a velocity which is the resultant of V2 and minus V1. This is V2. This is minus V1. The resultant of these two velocities would be this, which is V2 plus minus V1, which is velocity of B as seen by A. It's as if A is fixed and B is moving with this velocity. Now, it's as if A is fixed and B moves with this velocity. So, if A is fixed and B has a velocity, then do you realize that if this velocity is directed from B to A, B will collide with A? Yes or no? That means what we need is velocity of B with respect to A must be along BA. Velocity of B with respect to A must be along BA. This resultant must be along BA so that BA eventually bumps into A. Yes or no? That means VBA, which is like V2 and minus VA, resultant of V2 and minus V1. What is this vector BA? This vector BA is actually final position minus initial position. Final position vector minus initial position vector. That's R1 minus R2. Do you realize that R1 minus R2 must be parallel to VBA? R1 minus R2, this vector must be parallel to VBA, right? For them to collide. So R1 minus R2 must be parallel to VBA. If these are parallel, that means a unit vector in this direction must be the same as a unit vector in this direction, right? So first of all, R1 minus R2 must be parallel to VBA. That means VBA is V2 minus V1. That means a unit vector in this direction must be the same as unit vector in this direction. If two vectors are parallel, then a unit vector in this direction must be the same as a unit vector in this direction. Yes or no? That means R1 minus R2 by mod R1 minus R2. That's a unit vector in this direction. That must be the same as a unit vector in the direction governed by V2 minus V1. Unit vector along V2 minus V1 is like V2 minus V1 divided by mod V2 minus V1. So if the four vectors R1, R2, V1, V2 are related by this condition, then the two particles must collide. Then the two particles must collide. Yes. Yes or no?
Yes, sir.
Let's also handle this problem without deploying relative velocity notion, right? Relative velocity is only a tool that we have learned so that we could effectively use it, but doesn't mean that you should be handicapped in absence of this tool, because everything goes down, percolates down to the basics, right? Same first principles. So you should never feel handicapped in the event you don't know a tool, because you could still go from first principles and solve the problem, right? So let's solve this problem using first principles without deploying the relative velocity notion at all. Clear? We'll find the same condition for which the two particles will collide. Clear? Particle A with position vector R1 moves with velocity V1. Particle B at the same instant of time with position vector R2 moves with velocity V2. Right? Now, if they have to collide, say they collide at a certain point P. They collide at a certain point P t seconds later. T seconds later they collide at a certain point P, the two particles. And let's say the position vector of this point is R. R is the position vector of this point, right? Now A must have moved in this direction for t seconds. A must have moved in this direction with a velocity v1 for t seconds. So that means this displacement, first of all, this is r1, this position vector is r2. This vector must be v1t. This vector must be v1t, yes or no? Yes, similarly, B moves with a velocity v2 for t seconds in this direction. So this vector must be v2t. Don't do it. Yes or no? Yes. Right? Now, do you realize r minus r1 is v1t? This vector is what? Final position r minus initial position r1. R minus r1 is v1t, right? R minus r2 is v2t, where t is a scalar. T is a scalar. Yes or no? right? If I subtract these two to eliminate r, then what do I get? I end up getting r2 minus r1 equals v1 minus v2 into t, where t is a scalar. That means if a vector A is k times a vector B, then A and B must be parallel vectors. If k is a positive scalar, if A is k times B, A and B must be parallel vectors. So this is a vector A, this is a vector B, this is a scalar k. So A is k times B, that means A and B must be parallel vectors. So which means R2 minus R1 must be parallel to V1 minus V2. If these two vectors are parallel, then unit vectors in their direction in the direction of these vectors must be the same, right? So this would mean R2 minus R1 by mod R2 minus R1 must be V1 minus V2 mod V1 minus V2. That's the condition for the two particles to collide. Clear? All's good? Now, suppose this is the origin of coordinates, and there is a particle moving in this direction with a velocity of, say, 10 kilometers per hour. Right? And there is a particle P, which is, say, 10 kilometers initially. This is at time t equal to 0. This is also time t equal to 0, which is 10 kilometers from O, and say is moving in this direction with a, this is 10 kilometers. Distance between O and P, 10 kilometers, and there is this particle at time t equal to 0, which is moving in this direction with a velocity of, say, 10 kilometers per hour. Right? Now, t seconds later, O would have gone to O prime. Say t hours later, this would have covered a distance 10t. This would have covered a distance 10t kilometers in t hours, right? Whereas this particle P would have gone from P to P prime, and it would have covered 10t kilometers in this direction. So t hours later, P is here and O is there, right? And very clearly, again, as you can see, this distance is going to be 10 kilometers, which was originally known, minus 10t. So this is going to be 10 minus 10t. Yes or no? Yes, right? This then is the new separation between the two particles. This is the new separation between the two particles t hours later. And what is s squared? S squared is going to be 10t whole squared plus 10 minus 10t whole squared. That's the separation between the two particles t hours later. Right? As t changes with the passage of time, the separation between the two particles will change with time. Right? I now want to find out a value of t. I now want to be able to find out a value of t for which S's separation between the two particles is the least. You know what I'm saying? To find t for which S is S least, the separation between the two particles is the least it could be. Clear? Now, one thing, I could use algebraic manipulation here and find t, could use calculus and find t for which S square is the least, but I will not do all that. I'm going to take recourse to reducing this problem to an equivalent relative velocity problem and solve this problem in the relative velocity domain. We want to find the time in which the separation between the two particles becomes the least, and what's the least separation that's possible. What is the least S square? What is the least S between the two particles during this journey? Clear? Now, so you've understood the problem, right? Now let's reduce this problem to an equivalent problem. Clear? Let me look upon O as an observer. O is fixed. Then the velocity of P would have to be modified. Velocity of P would be velocity of P minus velocity of O then. Yes or no? Right? So, I pin this observer O. Then, P would have a revised velocity. It will no longer be Vp. It will be Vp minus Vo. Vp is 10 kilometers per hour like this. To the velocity of P, I must add negative of the velocity of O. Velocity of O is like this, 10 kilometers per hour leftwards, but negative of the velocity of O would be 10 kilometers per hour rightwards, right? So this would be negative of the velocity of O, which would be 10 kilometers per hour to the right. Yes or no? So to the velocity of P, if I add negative of the velocity of O, I would get velocity of P with respect to O. With respect to O means it's as if O is an observer. It's as if O is pinned and fixed. And it's as if P now has a velocity governed by the resultant of these two. Such would be the velocity of P, yes or no? So, velocity of P then would be like this. P would move in this direction. P would therefore move in this direction. And the velocity of P as seen by O, this is 10, this is 10, this is going to be 10 root 2. 10 root 2 kilometers per hour would be the velocity of P, and this angle would be 45 degrees as you can see. So P would now, as seen by O, move with the velocity of 10 root 2 kilometers per hour, making an angle 45 degrees as shown. How about it? Right now? So P has a velocity in this direction, a velocity of 10 root 2 kilometers per hour, going this way. O is fixed. That's an equivalent problem, right? It's as if O is fixed and P is moving with a velocity of 10 root 2 kilometers per hour along this direction at an angle of 45 degrees as shown. What do you say? Make sense to all of you? Now, if P moves in this direction and O is fixed, then during this journey of P, do you realize that this would be the shortest distance between O and P? Perpendicular distance? This will be the shortest distance between O and P? Yes or no? OM would be the shortest distance between O and P. The perpendicular distance, isn't it? right now? Huh? And this we know is 10 kilometers. See, this is 10 kilometers. OP is 10 kilometers. Then do you realize that OM is going to be 10 sine 45 degrees? 10 sine 45 degrees? Right? So OM, shortest distance, is going to be 10 sine 45 degrees, which is like a 10 by root 2 kilometers. That's the shortest distance. Yes or no? Right? Now, let's say the time taken to reach the shortest distance, t. Realize that the velocity of p in this direction is what? 10 root 2 kilometers per hour. And what is this length? This length is 10 root 2 kilometers. Isn't it? 10 by root 2, 10 cos 45 degrees. Isn't it? PM is 10 cos 45 degrees, which is like a 10 by root 2 kilometers. And this distance is covered at the rate of 10 root 2 kilometers per hour. Yes or no? This distance is covered at the rate of 10 root 2 kilometers per hour. So the time taken to cover PM, 10 by root 2 at the rate of 10 root 2 kilometers per hour would be these many hours. Yes or no? Yes, half an hour, 30 minutes is what you get. In this time, the distance between them attained is going to be the shortest possible. Clear? Confused or all right? Stand by.